For centuries, the scientific consensus was straightforward. Earth had clear biological boundaries. Venture too deep into the darkness, too high into the freezing altitudes, or too far into toxic geology, and the landscape became completely sterile. Look at a place like this. The extreme acidity and heavy metals present in these waters create conditions that dissolve most biological structures on contact. It looks like a place where biology cannot function. The traditional recipe for a habitable environment relies on a very specific set of ingredients. Organisms require abundant sunlight, mild temperatures, and easy access to organic energy to survive and reproduce. Yet researchers continuously pull samples from these seemingly dead zones and find them crawling with microbes. Nature operates with a completely different rulebook, supporting organisms that thrive in environments lacking every traditional biological necessity. Finding these extremophiles requires us to discard our old maps and redraw the absolute physical boundaries of where biology is capable of taking hold. Consider the deep ocean floor. Thousands of meters below the surface, the atmospheric pressure is crushing, and the environment is locked in absolute permanent darkness. But at the tectonic boundaries, we find hydrothermal vents. Here, superheated water infused with metals and minerals erupts directly from the Earth's crust into the freezing ocean. Specific microbes gather around these vents and perform chemosynthesis. They pull hydrogen sulfide and other chemicals directly from the erupting water, oxidizing them to produce their own cellular energy without a single photon of sunlight. This biochemical workaround is highly efficient. The energy these microbes produce is substantial enough to support massive, complex food webs deep in the abyss. Entire communities rely entirely on this microbial foundation. Animals like these giant tube worms grow in dense clusters, adapted to withstand the heavy metals and intense heat, living completely off the chemosynthetic bacteria housed inside their own tissues. The existence of this ecosystem demonstrates that biology can decouple entirely from the sun. Heat and geology alone can power a sprawling, dynamic environment. Back on the surface, we find environments defined by extreme toxicity. The water in Spain's Rio Tinto is heavily acidic and packed with dissolved iron and other heavy metals. The microbes living in this river consume sulfide minerals as their primary fuel source. In doing so, they excrete sulfuric acid as a byproduct, directly generating the harsh chemical conditions of their own habitat. While surface extremophiles feast on rocks, organisms buried beneath the ocean floor face a different challenge: absolute, prolonged starvation. To access this buried biosphere, researchers must deploy massive scientific operations. Ships like this one drill hundreds of meters down into the compacted sediment layers below the seabed to extract core samples. In these deeply buried sediments, the microbial strategy is extreme slow-motion metabolism. Deprived of fresh organic matter, they slow their processes to a near halt. The availability of energy is so severely limited here that a single cell might only divide once every few thousand years. They are not actively growing or expanding their territory. They are merely persisting in a dormant state. We often picture life as a constant drive to multiply, but in the deep sub-seafloor, ultimate biological success is simply mastering the ability to persist on the absolute minimum amount of energy required to not die. A similar endurance test plays out in the Antarctic dry valleys. This landscape combines freezing temperatures, severe nutrient scarcity, and hyper-arid conditions that strip moisture away from exposed surfaces. To survive this severe surface exposure, certain microbial communities become endolithic. They retreat inside the rocks themselves, sheltering within microscopic pores where tiny amounts of moisture get trapped and the cells are slightly insulated. Escaping the cold is only half the battle. Extreme desiccation, combined with background ionizing radiation, inflicts severe physical damage at the cellular level. Radiation punches directly through a cell's core operating instructions, snapping and shattering the DNA helix into dozens of scattered fragments. For a typical organism, hundreds of double-strand breaks in its genetic code mean immediate cell death. Yet the bacterium Deinococcus radiodurans regularly survives this exact scale of catastrophic genetic destruction. It accomplishes this by keeping multiple, tightly packed backup copies of its genome on hand. Highly efficient repair enzymes then sweep in, using the intact copies as templates to ensure the shattered fragments are rapidly stitched back together in perfect order. Deinococcus radiodurans did not evolve specifically to live inside nuclear reactors. This intricate repair machinery is an evolutionary response to severe, long-term desiccation on Earth, which produces similar DNA damage to radiation stress. Nature's most resilient organisms aren't built to be invincible against damage. Instead, they rely on unstoppable biological systems for relentless cellular repair. These organisms don't possess evolutionary superpowers. They are entirely bound by the exact same laws of chemistry and physics that govern all biological material. They simply utilize alternative methods of biochemical accounting. Finding microbes that eat rocks or survive deep freezing here on Earth does not prove that alien life exists on planets like Mars or below the ice of ocean moons like Europa. It does, however, expand our scientific dictionary. By studying extremophiles, we widen the strict parameters of what constitutes a habitable zone. Instead of a narrow, delicate set of conditions based on sunlight and mild weather, the boundaries of potential life are expanding outward, encompassing environments once thought impossible to endure. Studying Earth's extreme biological analogs teaches astrobiologists how to look for chemical signatures, and more importantly, where they are scientifically justified in pointing their instruments. Long before we search the stars, the evidence beneath our feet shows that life on Earth is far wider, deeper, hotter, and colder than we ever imagined. If you enjoyed exploring the absolute limits of biology, share this video with someone who loves a good scientific anomaly.
Share this with someone who loves fun facts.